So let's go ahead and let's talk about solubility, the equilibria associated with solubility, and the solubility product. So why do we care about solubility? Well, solubility actually impacts a lot of things that we interact with on a daily basis. So things like food flavoring. When we dissolve sugar and salt into water, basically those ions or those molecules that have been placed in water are then able to permeate our food and give our food specific flavor profiles that make them tasty. Areas where solubility also maybe are kind of less intuitive is the thermal efficiencies associated with equipment that basically heats our water. And so like calcium sulfate, for instance, is less soluble in hot water than in cold water. So what ends up happening is that the tubes and the surface inside boilers that produce hot water in large buildings and things of that sort can end up having coatings that are basically affecting the ability for the transfer of heat into the water and subsequently lowering the efficiency of your boiler. You also see solubility being a factor when you see the soap scum that builds up on your shower door. Basically that film, that white film that builds up, is caused by the solubility differences in hot water versus cold water, as well as how those ions interact with the soaps and stuff that you use to wash your body. Other areas where solubility is concerned or utilized is basically x-rays that are done for the gastrointestinal tract. So what we do is basically we consume a solution that contains barium, but barium ions by themselves in our body are very toxic, so they're not good for us, but they're really good for helping with the x-ray procedures. So basically by consuming barium sulfate, we can clarify the x-ray, and so that we can actually see how the intestines and such actually look. But we also are not putting a bunch of barium ions into our body because barium sulfate is really, really insoluble. Okay, so basically we take advantage of the low solubility of barium sulfate to allow us to increase our x-ray capabilities, and therefore obviously the solubility issues impact not just food flavoring or water heating, but also medical applications. So solubility also affects our teeth, right? So this is a big deal here. So tooth enamel basically has hydroxyapatite, which is consists of this molecule here. Obviously has calciums and phosphates and hydroxides. And what ends up happening is that this enamel is soluble in acids that are present in our food. Okay. Now the neat thing about that process is that obviously if we eat a bunch of highly acidic food, or don't brush our teeth and allow those bacterium to produce acids that break down our tooth enamel, we subsequently get cavities. However, we figured out that fluoride, basically that F minus, allows us to replace the hydroxides that basically get released, and basically allows us to replace them and produce calcium fluoride. And calcium fluoride is much less soluble than the original enamel, and you subsequently basically get a nice little filler or replacement on your tooth. So basically what you're doing is replacing the hydroxide ions with these fluoride ions, and subsequently producing a less soluble compound in the acidic situation, and subsequently taking advantage of this fluoride's properties in conjunction with calcium, and therefore producing the nice result of not having to go to the dentist to go get fillings. Okay, so fluoride in your toothpaste or in your mouthwash can really help you avoid spending some time at the dentist and getting a filling. So let's go ahead and talk about what happens when we add ionic solids to solution. So basically, if we look at the surface over here, this is the surface of the ionic solid. So what ends up happening is as we drop that ionic solid into water, what ends up happening is the water molecules start to surround the individual ions and isolate them in their aqueous ionic form. So basically, in this case with the calcium fluoride, when you add it to water, your calcium +2 ions and your F-1 ions, or your fluoride ions, break apart and subsequently get surrounded by water molecules. Now, typically, many ionic solids dissociate completely, and you get, complete ionization. So in this process, guys, initially you don't have any ions in solution, but as this interaction proceeds, as these water molecules come and separate out these ions, what ends up happening is you have these floating ions in solution. However, what ends up happening is that as the amount of calcium +2 and F- ions are in solution, as that increases, there's a higher likelihood that those ions could potentially bump into one another and reform that calcium fluoride. So basically, these two processes, the dissociation process and then that collision process and the reformation of the calcium fluoride, basically reaches equilibrium, okay? And that dynamic equilibrium process where we're putting ions into solution and then reforming the calcium fluoride, it's a process that we've talked about, multiple times. We've talked about these ionization processes. In this case, though, what we're looking at it with respect to is ionic compounds specifically and their solubility process. So this brings us to another K, okay? And so basically we've talked about K, for several chapters now. And basically when we write our K value here for the ionic compound, and its basically ionization or solubility in water, we write K sub Sp, and that's known as the solubility product constant, or just solubility product. Okay, and so when we write our Ksp equilibrium expression, obviously we're going to follow the rules that we have in the past. Notice that the Ksp for this specific ionization process only has calcium ion and fluoride ions because, remember, we only include aqueous substances. We don't include pure solids or liquids. And notice also, obviously, I've squared the fluoride component because there's a coefficient of 2 in front of that in the balanced equation. Okay, so our equilibrium expression is represented in this way. We follow those heterogeneous equilibrium rules, and we indicate that this is the solubility product constant by this subscript Sp. Now, I do want to mention that the amount of solid and the size of the particles that are present, so if they've been, if they're in big chunks or if they've been, finely ground, that's not going to affect the position of the equilibrium. Okay, now stuff might dissolve a little more quickly, but in terms of the concentrations of ions and such that you would have in solution relative to the amount of your solid is going to remain consistent. Okay, so differentiating between solubility and solubility product. The solubility product, guys, is an equilibrium constant. Basically, it's going to have only a single value for a given type of solid at a given temperature. Solubility, on the other hand, is an equilibrium position, and that can actually change depending on, whether you have the presence of or absence of a common ion. We can use Le Chatelier's principle to affect the solubility of our substance. So what you should understand is that the numeric value of your solubility can actually change depending on what else is present in solution. However, your Ksp value is going to be constant at that specific temperature. So let's go ahead and let's calculate Ksp from solubility. So what they've told us here is that I have copper 1 bromide, and that it has a measured solubility of 2.0 times 10 to the negative 4 molar. Okay, notice this is my concentration value, this is my solubility. Okay, so what they've given us here is our initial concentration of copper 1 bromide. Okay, and so we take that value, And we're going to plug that into an ice table. But before we plug it into our ice table, we want to know what components we have in our ice table. So copper 1 bromide, we have that as our solid. And what we're assuming is that it ionizes completely into copper +1 and bromide ions. Okay, we then set up our ice table accordingly. Okay, just like we have in the past. We plug in our initial concentration of what we know, which is copper 1 bromide. Okay, we're going to assume that initially we have no copper +1 or bromide ion. Okay, we indicate the changes that we would expect. Okay, and we are going to assume 100% ionization because this is an ionic compound. Okay, so we're going to assume that copper bromide no longer exists and that we only have copper +1 and bromide or bromine -1 ions present in solution. Okay, so then we take these concentration values and we plug them into our equilibrium expression, which will be written as follows. Okay, once again, we leave out the solid because they don't get included into equilibrium expressions. We plug in our concentration values of our copper +1 and bromide ion into the equilibrium expression, multiply them together, and we get the following value for our Ksp. Okay, and just like other equilibrium constants, the units are usually going to be omitted. Okay, so we haven't included them there. Okay, so let's go ahead and look at a different example. Bismuth sulfide is Bi2S3. It has a measured solubility of 1 × 10⁻15 molar at 25 degrees C. They want us to calculate the Ksp. Same process here, though. I want you to notice that we've written out the ionic compound and subsequently the ions and quantities that it would break into. Okay, we set up our ice table. Okay, we put our initial concentration of our ionic compound and corresponding ions. Okay, notice that we indicate the changes. Remember, 2x and 3x is coming from those coefficients. Okay, we're also assuming that this process is going to go to completion, right? So if x is equal to the difference between these two values, you're going to end up with 1 × 10⁻15. And if we plug those into our two ions, we get 2 × 10⁻15 and 3 × 10⁻15 respectively. Okay, we take those values, we plug them into our equilibrium expression that we see down here. Okay, notice we only include those ions, and also don't forget that we have squared and cubed the ions respectively because that's how we set up our equilibrium expressions. We plug in those equilibrium values, do our calculation, and we subsequently get our Ksp value. Notice that your Ksp value here is very small, with 10⁻⁷ as being your order of magnitude. Okay, so basically, guys, there are a couple examples of calculating Ksp from solubility. You're making the assumption that the solid ionizes completely, and you're basing that off a measured solubility value that you know. Now, the Ksp value that we get in this situation, as I said, is very small, so that's indicative of a solid that isn't going to be very soluble in solution. Okay, but as you can see, this is the approach that we take when we're calculating. Okay, so now we're going to go the opposite direction, and we're going to calculate solubility from Ksp. Okay, so they've given us a Ksp value for copper 2 iodate. Okay, and they've told us that it's 1.4 × 10⁻⁷ at 25 degrees C. And they want us to calculate the solubility at that same temperature. So basically, we first write out our equation. So basically, we take our copper 2 iodate and break it into the ions that it would break up into. And we plug in our initial concentrations into our ice table. Remember, X is what we're trying to solve for. We want to know that value, or that solubility value for our copper 2 iodate. We're going to assume that our initial concentrations of our copper 2 plus and iodate ions are 0. Okay, we have the corresponding change values. Okay, and we assume still 100% ionization process that's going to occur with that salt. That's just the way we approach the problems. Okay, we have our corresponding X values. We now write our equilibrium expression. So Ksp is equal to the concentration of Cu2 plus and the concentration of our iodate ion squared. Okay, and we subsequently plug in our appropriate values for X. Okay, we plug them in. And that's going to be set equal to our Ksp value. We solve for X, okay, which we end up with 4x cubed being equal to 1.4 times 10 to the negative 7. Okay, divide out that 4 and take the cube root, and our x value is subsequently 3.3 times 10 to the negative third. And that is the corresponding value for our solubility of copper iodate, or excuse me, copper 2 iodate. So in this case, though, we also want to be looking at this with the appropriate units, right? This is concentration. So our x value is actually going to be a molarity value. And if we wanted to figure out any additional information, like how many grams of copper iodate that is, or how many moles, we could subsequently figure that out based on the knowledge of our solution volume and things of that sort. Okay, so relative solubilities of salts can be compared, generally speaking. The biggest Ksp value is going to be the most soluble. However, we do have to consider one thing, and we have to consider if we are comparing salts that produce the same number of ions in solution. Okay, if you have the same number of ions being put into solution, then you can make a direct comparison, and the one with the biggest Ksp will subsequently have the largest solubility, or be the most soluble. Okay, so if we look at an example where we have 3 salts that all put the same number of ions into solution, okay, Ag and silver iodide, it forms 2 ions in solution, copper 1 iodide, 2 ions in solution, and calcium sulfate also puts 2 ions into solution. So since they put the same number of total ions in solution, we can compare these Ksp values. Okay, the calcium sulfate has the largest Ksp value, so it's the most soluble. The silver iodide has the smallest Ksp value, so it's the least soluble. Okay, and subsequently you can make these comparisons directly when the same number of ions is present. So this is the caveat to that comparison. So what if the number of ions that are put into solution are not the same? So how do we compare these? Okay, so what do? Basically, if we have a different number of ions, okay, we have to make an indirect comparison. So what we have to do is we have to determine x, and we saw how to determine x, or that solubility, in the last example problem that we just did. Okay, so obviously some additional information would need to be provided in addition to our Ksp values, but we could subsequently find our x values in that same way that we did with the copper 2 iodate, and then compare those x values to decide which one has the largest relative solubility. So if we look at this, Bi2 S3 is the most soluble, even though it has the smallest Ksp value. So when they put a different number of ions, you can't make a direct comparison. You need to find that solubility value and make that subsequent determination based on the solubility values, not the Ksp values. Okay, so make sure that you guys are keeping that in the back of your mind for quizzes and tests in the future. So let's go ahead and let's look at how having a common ion present, so basically dissolving your solid into something other than pure water, can actually affect the solubility of your solid. Okay, so we've been told that we've dissolved solid silver chromate with a Ksp equal to 9 times 10 to the negative 12 in a 0.100 molar solution of silver nitrate. Okay, and so in this case, we want to know what the solubility of our silver chromate is. Okay, so we set up our ionization process that we see here. So we have our silver chromate, okay, we have our silver ions that breaks up into, we have our ice table. Okay, we don't know what the solubility of our silver chromate is. That's what we're trying to figure out. We know that initially we have the presence of silver because we were told we have a 0.1 molar concentration solution of silver nitrate that we're actually dumping our silver chromate into. Okay, and then obviously we say that our chromate value, chromate ion value, is 0 at our initial point because we're assuming no ionization has occurred. Okay, our C values, our change values, are going to correspond to our coefficients. Okay, and we subsequently are going to end up with a value of 0 of equilibrium for our silver chromate because we're assuming that it ionizes completely. Okay, and so our values for our equilibrium concentration of silver ion is going to be 0.100, okay, plus 2x, right? And our chromate ion value is going to just be X. Okay, so we look at our equilibrium expression, our Ksp expression here, and basically that occurs as follows, right? We have our silver ion squared times our chromate ion. Okay, we subsequently plug in our equilibrium concentration values for those units that are necessary, and we set that all equal to our Ksp value that's been provided. Okay, so now what we need to do is we need to solve for X. So we could go ahead and go do the long way and FOIL out all those values and solve for X, or we can check if we can do the simplification procedure. So if we drop out our X value that's associated with the change in our silver ion concentration at equilibrium. So what we've done is we've dropped the X, so basically simplified. Okay, so basically that value is still approximately equal to 9 times 10 to the negative 12. Okay, if we go ahead and take our squared component and divide it out, we'll get X all by itself, and we get 9 times 10 to the negative 10 as our X value. And as usual, we take this and this X value and compare it to our concentration value that we were given. The 5% rule applies, so this assumption is acceptable. So what we've calculated here is X, which is the solubility of the silver chromate ion in the presence of this silver nitrate salt solution. So basically what we did is we wanted to figure out how the solubility of silver chromate is affected by adding it to a solution that already contains a silver ion. Okay, so let's see how much of an impact that actually had. So if we go ahead and look at the solubility of silver chromate in pure water versus in the experience or the example that we just did with the common ion, we notice that our values for X, our solubility values, are going to be drastically different. Okay, so what does that mean? Basically, if we see that the solubility of silver chromate is much higher than in a solution already containing a silver ion, we know that the common ion effect is what has lowered our solubility of the silver chromate. Okay, so basically what's happened is by adding that silver ion, we've shifted our equilibrium to the left and decreased the solubility of the silver chromate. Okay, and that's what we would expect based on our understanding of the common ion effect and Le Chatelier's principle and all that good stuff. Okay, so let's do another example. Let's calculate the solubility of calcium fluoride in the presence of a 0.025 molar sodium fluoride solution. Okay, so calcium fluoride, we're trying to figure out to what degree or how soluble it is, what its solubility value. Okay, it breaks up into calcium plus 2 and fluoride ions. Okay, we set up our ICE table. Okay, we're trying to find out X. We're assuming that the ionization of calcium plus 2 initially is 0, and we're plugging in the 0.025 for the fluoride ion based on the 0.025 molar concentration of sodium fluoride that's in solution. Okay, now our changes in C are as follows, right? We're going to decrease by X, we're going to increase by X, and we're going to increase by 2X. Okay, so our concentration values at equilibrium correspond to X and 0.025 plus 2X. Okay, we write out our equilibrium expression, which is Ksp equaling the following calcium plus 2 concentration times fluoride ion concentration squared. We plug in the equilibrium concentrations, at least the values that we have, and we set that equal to the 4 times 10 to the negative 11, which is the Ksp value that they gave us. Okay, we can make some assumptions here. Obviously, we'll need to check our 5% rule. It is valid in this case, but basically we drop the 2x here. We solve for X down here. We get 6.4 times 10 to the negative 8. So the solubility of calcium fluoride in a 0.025 molar sodium fluoride solution is as we see here. So we've talked about how the solubility of an ion, or excuse me, the solubility of a salt can be affected by the presence of a common ion. So now we're going to go ahead and look at how pH can affect that solubility. Okay, so pH can affect solubility because it can alter the presence of species that do show up in solution. So magnesium hydroxide, okay, we know that that's sometimes used to treat upset stomachs. Okay, so the magnesium hydroxide, we chew up our pills or whatever, put it in our tummy, and it ionizes a little bit, 2 Mg plus 2 and 2 hydroxide ions. Now, if we increase the pH, right, so if we make this solution, quote unquote, more basic, what we're going to end up doing is increasing the number of hydroxide ions. If we increase the number of hydroxide ions, we're going to shift to the left. Okay, now if we decrease the pH, okay, so basically if we add H plus ions to this solution containing magnesium hydroxide ions, the H plus is going to interact with the OH minus to produce H2O. And basically that's kind of the equivalent of pulling hydroxide ions out of solution. And as we know, if we remove products, okay, our equilibrium is going to shift to the right. Okay, so by having an acidic pH in this situation, what ends up happening is we drive the ionization process of the magnesium hydroxide and therefore increase the solubility of this solid. So another example here, we have silver phosphate. Okay, it ionizes into silver ions and phosphate ions. Okay, now if we decrease pH by adding H plus ions, we're actually going to end up increasing the solubility of the silver phosphate. And the reason why is because the H plus ion is going to interact with the phosphate to form HPO4 minus 2. And this happens because PO4 3 minus is the conjugate of a weak acid, so it behaves as a base in solution. So when we add H plus to solution, it's going to want to interact with that H plus and subsequently produce this new ion. So that's basically the equivalent of pulling this out of solution. As we pull that out of solution, we shift the equilibrium to the right and subsequently increase our solubility. Okay. Another example here, silver chloride. Okay, if we decrease the pH, so basically add our H plus, that's not going to affect the solubility at all because the conjugate base of a strong acid is never going to want to interact with that H+, so we're never going to pull chloride ions out of solution and cause that shift. Okay, so here, as you can see, is a little bit of a combo of our conjugate acid base theory that we've been discussing for the past little bit. This right here is a weak base because it's the conjugate of a weak acid, right? So it can behave as a base in solution, while this is the conjugate of a strong acid, which is not going to behave as a base in solution at all. Okay, so there's not going to be that shift in this reaction, but there will be a shift in this one here. Okay, so some generalized rules for pH and solubility. Okay, so if the anion, like we just talked about the phosphate and the chloride example on this last slide, okay, if it's an effective base, so if it acts as a base in solution, i.e. it is the conjugate of a weak acid, when I add H plus or decrease the pH, the salt, the original salt, is going to show increased solubility in that acidic solution. Okay, so if the conjugate, or sorry, if the anion that you have present from the salt is the conjugate base of a weak acid, then generally speaking, if you acidify the solution that salt is in, you're subsequently going to get a higher solubility. Okay, and an everyday example of this feature or this concept is basically we see the increased solubility of carbonates in limestone caves. So what ends up happening is that CO2 that basically gets released into the underground water, or excuse me, the groundwater, basically makes the water kind of acidic. And because it's kind of acidic, what ends up happening is we increase the solubility, of the calcium carbonate, because the carbonate ions basically interact with the acid that's present, and you subsequently get a higher solubility of the calcium carbonate salt. Let's go ahead and look at precipitation and qualitative analyses. Okay, so we're going to talk about the ion product Q. So just like, this is going to be just like Ksp, except we're going to be using the initial concentrations of the ion. So this is very similar to the Q value that we've discussed earlier. Basically, we're not using equilibrium concentrations, we're using the initial concentrations. And basically, we use these to consider the formation of a solid. So basically, we're looking at the reverse process. Okay, so if we look at a specific example, calcium fluoride breaking up into its ions, our Ksp expression is going to be written as follows. Our Q, our ion product expression, is going to be written as follows. Notice the not symbols indicate that the concentrations we are plugging in are in fact initial values. Okay, so we've seen this before. Basically, if our Q value is greater than Ksp, precipitation is going to occur. Okay, and basically this precipitation process will continue to occur until equilibrium gets established and our Q value is equal to Ksp. If Q is less than Ksp, then no precipitation is going to occur. So basically, this type of comparison will allow you to decide whether or not a precipitation will form. Okay, so let's go ahead and look at this example. So does a precipitate form when 0.10 liters of 8 times 10 to the negative third, sorry, these should be exponential, molar lead nitrate is added to 0.40 liters of 5 times 10 to the negative third molar sodium sulfate. Okay, so what we're first going to do is obviously determine our initial concentrations of our lead and sulfate ions. Now, some of you may be asking, well, how did I know I'm dealing with the lead and the sulfate ions? Well, guys, let's first of all analyze what we've done here. First of all, we've taken a lead nitrate solution and a sodium sulfate solution, and we've mixed them together. So Pb, NO3 plus Na2SO4. All right, they've come together. These are both aqueous solutions. Okay, they're hanging out. Now, when we mix them together, okay, we obviously are hoping to get some precipitation. Okay, and based on the solubility rules from the solubility table, okay, we're going to end up with lead sulfate, okay, solid, and sodium nitrate, aqueous. Okay, so how did I know that this was going to be the thing that precipitates? Well, I know my solubility rules, or I went and looked at the solubility table. These are things you should go and acclimate yourself to. And basically, these are the ions that I'm actually concerned about because they're the ions that are involved in the precipitation. Okay, so first of all, what we need to do is we need to analyze the process that is occurring for this precipitation. Okay, so this lead sulfate, PbSO4, okay, is going to break into Pb plus 2, okay, oops, plus 2, plus SO4 2 minus. Okay, so those are the species that we're paying attention to, and the species that we can actually get values for. Okay, so that allows us to write our Q value, or expression, as follows. Okay, so if we go ahead and we calculate our initial concentrations of both the lead ion and the sulfate ion, we can subsequently calculate Q. Okay, so the Pb plus 2 ion, what I'm going to do is I'm going to take my initial molarity, okay, I'm going to multiply that by my initial volume of that solution that I added. So this is volume. It's that 0.10 liters. This is my molarity. Okay, and then I'm going to divide that by the total volume of my new solution. So notice that's the summation of both the volumes of my lead nitrate and my sodium sulfate solutions. Okay, I'm going to do that same thought process for my sulfate ion. Okay, I plug those in, and I subsequently get these two values for my initial concentrations of lead and sulfate ions. I take them over to their various spots in my Q expression. I plug them in, and I get my Q value. I'm then going to compare my Q value to my K value. So where would I get my K value? Well, the Ksp values for lead sulfate and a bunch of other options are available in the back of the book. Okay, so if you went to Appendix D in the back of your book, you'd be able to find those values. And the Ksp value that they have listed for lead sulfate in the back of the book is 6.3 times 10 to the negative 7th. Okay, so that definitely is smaller than the Q value. So since Q is bigger than K, lead sulfate is actually going to precipitate in this situation. Okay, so we could actually get additional information from these types of problems. So they've told us here that we have a solution that's prepped by adding 100 milliliters of 0.05 molar lead nitrate to 200 milliliters of sodium iodide. And basically they want to know if lead iodide will precipitate, or lead 2 iodide will precipitate. And so they additionally want to know what the equilibrium concentrations of the ions will be. And first things first, we just proceed with the equilibrium processes that we're actually concerned about. So all we really care about is how lead 2 iodide is going to be behaving. Okay, so this is what we're looking at, right? We want to, of course, figure out our initial concentration values. Okay, so just like we did in the last example, we have our molarity of our lead solution, we have our volume. Okay, we divide by the total volume of the two solutions that have been added together, and we subsequently get our initial concentration of lead ion. Okay, we do the same thing for the iodide ion, and we get those initial values. We plug them into the expression that we see here, and we subsequently get our Q value. In this case, Q is bigger than Ksp, so lead 2 iodide is going to, in fact, precipitate. Okay, but they also want us to figure out the equilibrium concentrations of the ions. Okay, so we want to figure out how much iodide and lead ion are going to be present at equilibrium. However, we have to figure out how much initially remain after the precipitation process has actually occurred, because we know that that's in fact going to occur. So in order to figure that out, what we need to do is we need to first figure out how many moles of each of the ions we start with before the precipitation process. Okay, so basically we know that if we take our volume and our concentration of our original solutions, we can get our molar amounts, or actually not molar, but our mole amounts of each of the ions. Okay, and that's before. Now, after, obviously these two are going to interact with one another, right? And so this is going to change, so it's going to decrease by x, okay? And this one is going to decrease by 2x. Okay, and the reality of it is we know that this precipitates, so we're going to treat our lead ion as that limiting reactant. So we're going to say that it gets all used up. So X is therefore going to be the difference between these two. Okay, and what we end up with is 0.005 as our value for X. Okay, so that's going to end up giving us 0 moles. Excuse me, for our lead ion, okay? And if we go ahead and continue with X being equal to 0.005, okay, we can go ahead and plug that into our X value here, and what we end up with is 0.020 minus 2 times 0.005, which is going to give us 0.010 moles as our initial number of moles of our iodide ion. So notice, okay, we have 0 moles of our lead ion and 0.010 moles of our iodide ion after the precipitation of PbI2. Okay, so they're wanting us to figure out how much of these two ions exist at equilibrium. Okay, so now we need to adjust these initial values that we figured out, okay, for equilibrium values. So we've set up an ice table here. Notice I'm looking at the basically reverse process. The reverse process, what we just looked at on the previous slide. We were looking at the precipitation procedure, and now we're looking at the relationship of this salt, okay, to the relationship of the presence of these ions. Okay, so basically we set up our ice table. We can actually pretty much ignore our lead iodide because it doesn't show up in the equilibrium expression. Okay, so we said we had 0 moles of the lead iodide or lead ion after we precipitated out our lead iodide. Okay, but we also figured out that we had 0.010 moles of the iodide ion present after that precipitation procedure. So what we're going to do is we're going to take that number of moles and we're going to divide it by the total volume of solution after we've mixed both solutions. So notice this is increased to 0.300 liters. So basically make sure that this is the total volume here. Okay, now how is this stuff going to change? Well, we know that our lead iodide theoretically would put some lead and iodide ions in solution. Okay, these values of X should be positive and corresponding to each of the coefficients. So we have X and 2X respectively. Okay, bring that down, we get our equilibrium concentration values. We take these values and we plug them into our equilibrium expression. We know our Ksp value, so we can subsequently solve for X. Okay, now notice I've dropped off the 2X here when I've plugged it in. I'm going to assume that the X value there is pretty small with respect to the change. If you check that, you'll find out that that's an acceptable assumption. We solve for X, and X is therefore 1.3 times 10 to the negative 5th molar. Okay, so this is corresponds to the concentration of your lead ion at equilibrium. Okay, and our iodide ion can also be calculated as seen here. Okay, so we've calculated these two. So we were able to establish in the initial part of this problem that we would have a precipitation actually forming of this lead iodide. Okay, we then took that information and figured out how much of the lead iodide and, how much of the lead ion and the iodide ion would be present after the precipitation had occurred. Okay, we take that as the initial values of what we have here before equilibrium. Okay, and then we use our ice table to calculate our concentrations of our ions that remain at equilibrium. Okay, so basically the precipitation process does occur, but equilibrium does get established. Okay, so even though theoretically we should have used up all the lead iodide, all the lead ion to produce lead iodide, when equilibrium gets established, we actually do end up having a little bit of those ions still present. Okay, so what is selective precipitation? Selective precipitation basically is a procedure that allows us to separate out solutions, separate out mixtures of specific metal ions that are in solution by using an anion that will only form precipitates with, certain metals that are in solution. Okay, so an example would be if in this situation I have copper ions, or copper plus 1 ions, and lead plus 2 ions in solution. And basically when we want to know if the CUI or the PbI2 are going to precipitate first. And so we're going to figure this out based on some information we've been given. So we've been told the initial values of copper ion and lead plus 2 ion that we have in solution. Okay, and we have their equilibrium expressions, and we subsequently also have their Ksp values. Okay, so the Ksp value for the lead 2 iodide is actually 1.4 times 10 to the, negative 8th. Okay, and the Ksp for the copper iodide, okay, is 5.3 times 10 to the negative 12th. Okay, and so we can figure out which metal is going to precipitate first based on basically the concentrations that we know, okay, the equilibrium Ksp constants, okay, and we can subsequently compare our I values, okay. So the reason why the I values are important is because, first of all, that's the item that we are adding to this solution. Okay, and basically by adding iodide, we are going to be shifting potentially the equilibrium towards the left, right, towards that precipitation procedure. So once we find what the I values are for each of these substances at equilibrium, we know that by adding anything over that value, we will cause precipitation formation. Okay, and so when you calculate these, okay, we end up with actually a quite smaller I value for the copper iodide precipitation procedure than we do for the lead. So what ends up happening is that the CUI is going to precipitate first because we cause that equilibrium shift earlier because the iodide ion is needed in smaller quantities to cause that precipitation for that specific substance. So basically, selective precipitation, depending on what your Ksp values are and obviously your quantities, that's going to dictate how you can utilize selective precipitation to basically separate out substances. Okay, so guys, remember, as I was saying, this qualitative analysis approach, this, ability to see what type of ions you have present, or, who's going to precipitate first, is going to be based on your, basically, precipitation procedures. Okay, you're going to be considering the solubility components of those procedures. Okay, so guys, go and review your solubility rules for sure.